Okay, ladies and gentlemen, let's begin our lecture. Last time we discussed quantifiers. Among some others, the most important were the universal quantifier, which is denoted by such symbol, and which means that for each x that is from some predefined domain, for each x the property phi holds. So phi of x holds. So this is our intuitively understandable meaning of the universal quantification. For each x, phi of x holds. For example, for natural numbers, we have something like that. For each x, x is, say, less than x plus 1. Nice to see you. And also, we discussed another quantifier that is the existential one. So this was a universal quantifier. And this one is the existential. Why it is existential? It means that there exists some x from our predefined domain. Of course, there exists some x such that phi of x holds. So this is true for natural numbers, and I may write something like that. There exists x such that 2 x plus 1 equals 3. That's also true, of course. But if we had a universal quantifier here, this wouldn't be true. There is some difference between the two, okay? My voice is too low for Let's check it. And now, can you hear me clearly? I mean our distant students. So is it any better than it was before? What about the sound? Yes. What does it mean? Yes. Okay. Still no comments? Yes. I take it as that now the sound is better. Okay. So these quantifiers were discussed previously, and now let's see how one can use them to express some new meanings. For example, in mathematics, it's very usual to say something like that. There exists a unique x such that, as t, that means such that some phi of x holds. this is usually denoted the following way. They exist, then we have an exclamation mark. There exists a unique x such that phi of x holds. For example, there exists just one x in naturals, so that x plus 1 equals 3. But do we have any way to express this quantifier in terms of these two, which are considered basic? Is there any way to do so? In fact, it is. We say that there exists a unique x such that phi of x holds. What does it mean? First of all, that means this symbol, of course, reads is logically equivalent, is true if and only if. So they are logically the same. What does it mean? Of course, that means that there indeed exists such x. But not only that. How is it possible to express the following idea? This x is the unique. No other x, may one say. No other x satisfies phi. But what does it mean, other? Other means not equal. So no other, no x which is not equal, no y which is not equal to x satisfies phi. Or another way to say the same thing is as follows. Let's continue this line here. And for each y, whenever y satisfies phi, y must equal x. Let's think about it. What does it mean? There exists x such that x satisfies our phi, and each y satisfying phi equals x. So x is the unique one. So here, for example, we have that there exists x, which such that x plus 1 equals 3, and every y such that y plus 1 equals 3 is equal to x. Is it true? Of course. Which x can we take here? Why is this? Why is it true? We say that there exists some x. Which number can you take for x? 2. What else? Of course. But what do we have for 2? 2 plus 1 equals 3. Of course. And also for each y, if y plus 1 equals 3, then y equals 2. Do you agree with this one? That means that y is a unique solution to this equation. So we see that sum 2 satisfies this condition. So there exists x which does satisfy. Is it clear? So let's memorize this expression for the existence and uniqueness quantifier. There exists a unique x, that means that there exists such x, so that it satisfies our phi, and also every y that satisfies is equal to our x. What's next? In fact, one can express the universal quantifier in terms of the existential one, and vice versa. How is it possible to do so? The main idea is as follows. What does it mean that, say, every natural number is fragile? What does it mean that a natural number is fragile? We don't know. It means nothing. Some abstract property like phi. But more smooth language-wise, it's better to say that a number is fragile than it satisfies phi. Okay. What does it mean that every natural number is fragile? That means that it is not the case that everyone is fragile. That means that it's not the case that there exists a number which is not fragile. Everything is blue, if and only if it is not the case that there exists a not blue thing. Is it clear or not? And what does it mean that there exists a fragile number? That means that it is not the case that every number is not fragile. Is it clear? Okay. By the way, is there a natural number such that x equals x plus 1? Is there such a natural number? No such number. What does it mean? What does it mean that there is no such number? That it's equivalent to the following formula. Each natural number is not equal to x plus 1. Or I may put it the following way. For each natural number, it is not the case that it's equal to x plus 1. So in general, the negation of this existential statement is equivalent to this universal statement. Is it clear? There is no x with property phi. What does it mean? Every x does not satisfy property phi. So, what's your question? The first one, this one. Okay. We shall obtain it in a moment. At first, is this one clear? If two statements are equivalent, their negations are equivalent as well. So, that means that this statement is equivalent to this one. But what can you say about the following statement? It is not the case that A. It is the case that A, so it's equivalent to A. So this one is equivalent to our existential phrase. So these two are equivalent. Is it clear? Now, let's do the same work for the first. So, this one is explained enough, I think. So, now, let's see this one. Every natural number is less than 3. Is it true or false? It's false. So, what does it mean that it is false? That means that this one, it is not the case that every x, every natural x is less than 3. This one is true. But what does it mean that it is true? Not every x is less than 3. That means that some x is not less than 3. There exists some x, so that it is not the case that x is less than 3. How is it possible to refute a universal statement? In order to refute it, it's enough to give an example of an object which does not satisfy our property. There exists such x which is not less than 3. By the way, does it exist? Which natural number is not less than 3? Which one? 1 is not less than 3? Which number is not less than 3? 4, of course. So there exists such a number. Okay. And in general, you have that it's not the case that each x satisfies phi. That means that some x does not satisfy phi. Okay. But we know that if two statements are equivalent to each other, their negations are equivalent to each other as well. But double negation may be cancelled from a formula. So for each x, phi holds, that it's equivalent to the following. It's not the case that there exists some x for which phi does not hold. Is it clear? That's exactly our first formula. Any questions? And the last thing I want to discuss about the quantifiers is checking arguments employing quantifiers for validity. Okay, let's reiterate. An argument, a proof or something like that, is valid if and only if, whenever its assumptions are all true, its conclusion is true as well. Okay, now let's see the following argument. Every number, every natural number, by the way, it doesn't matter. In fact, every number is fragile. What does it mean that a number is fragile? It means nothing. But you may define to be fragile however you like. It is some abstract property. It's a substitute for writing phi. If number n satisfies some phi, or whatever phi you take, every number is fragile. It's our first assumption. Our first assumption. Okay. Every fragile number is blue. That's another assumption. And now I want to conclude from that. What can I conclude here? Any ideas? Every number is fragile. Assume it. Every fragile number is blue. What can you infer therefrom? So please. It means nothing. Fragile, that means, in general, that you can easily break it. Like a glass, say. But here that means nothing. It's some abstract property. Why do I use abstract properties? Why don't I say every number is even? Because then you would say me, you would say that, no, professor, that's not true. Not every number is even. This assumption is false. How could we assume that it is even when it how could we assume that it is true when it is false, in fact? But we don't like that. We want to think abstractly about some arbitrary property for which we don't know either it is true or false for every particular number. Assume that some natural numbers are fragile. Whatever it could mean. In mathematics, you may define terms. You may say, let us call a natural number fragile if it is, say, greater than 7. Oh. So, let's think abstractly. So, every number is fragile. Assume it. Then assume that every fragile number is blue. What is the most obvious conclusion from this two? Of course. So, this is our conclusion. Is this conclusion well grounded or not? If we imagine that these two are true, is it necessary that the conclusion is true as well? Of course. For whatever meanings our words fragile and blue could take, for whatever meanings, always. So what do we need in logic? In logic, we have to develop some procedures that guaranteedly preserve truth from any logically valid method should give us a true conclusion from any true assumptions. We don't know whether it is true or false. Why don't we know? Because we don't know what does fragile mean. But for whatever it means, if these two are true, then this one must be true as well. So this argument is valid. let's formalize it. Let's put it into symbols. Every number is fragile. How can I put it into symbols? For each x, f of x, where f of x means that x is fragile. And now let's formalize this one. How is it possible to put it into symbols that every fragile number is blue? Any ideas for each x? For each x? Every fragile is blue. An arrow, of course. We should have an arrow, but where? Somewhere in the middle. But what would be the first term and the last one? F of x. So if x is fragile, then it's blue, b of x. Oh, easier, isn't it? Okay. If x is fragile, then it is blue. For each x, it's our natural idiom in mathematics that allows us to say that every a is b. Say every number which is a multiple of 4 is also a multiple of 2, that is even. Or every fragile number is blue. Or every number which is greater than 7 is greater than 3. How is it possible to translate it into mathematical symbols? For each x, if x is greater than 7, then x is greater than 3. By the way, that's true for natural numbers. If you substitute any natural here, for example, I don't know, 1, you should obtain a true implication. If 1 is greater than 7, then 1 is greater than 3. Is this implication true? How could this one be true if its instance, its particular case is not true? It is true. Okay. When an implication is true. No. When the assumption is false or the conclusion is true. Here the assumption is just 1 is greater than 7. Is it true or false? So that's false. And from the false assumption, it follows anything. So this implication is true, of course. And our quantifier means that this would be true for whatever number one can substitute for x. Is it clear? And here we have something like that. For each x, whenever x is fragile, x is blue. And now let's finish this example and formalize our conclusion. How is it possible to do so? For each x, b of x, of course, that's it. And we see that it is logically valid. Whenever this one is true and this one is true, then this one is true. And now let's prove that it is logically valid. What should I prove? I have to prove that when our assumptions are true, the conclusion is true as well. Okay. When they are true, when I is false, this case is not interesting for us. We're not interested in that case. Assume that our assumptions are indeed true. It is not necessary to write that some statement is true. In general, when you write some statement, you say that it is true. It's a usual convention. You don't just mention statements, but you state them. When you write that x, that 2 plus 1 equals 3, you state it. You say, okay, that's the case. Assume that every number is fragile, and every number which is fragile is blue. I want to say, I want to prove, of course, that every number is blue. In general, how is it possible to prove a universal statement that every number is blue? Let's consider an arbitrary number. Prove that it must be blue, and then generalize. So, our proof. Let's consider an arbitrary. What does it mean, arbitrary? Arbitrary means nothing special. Let's consider an arbitrary number and call it n. But we know that every number is fragile. This was our first assumption, assumption 1. And this one was assumption 2. By our assumption 1, every number is fragile. Hence, n is fragile as well. So I may say that f of n. Is it clear? Why? It is true for each x and for our n as well. Why not? By assumption 2, I may substitute n here for x as well. If this implication holds for each x, it must hold for n. So now I have a true implication with a true assumption. An implication is true if and only if its assumption is false or its conclusion is true. Is it possible that the assumption of this implication is false? No! We know the assumption to be true. So the only possible reason for this implication to be true is that its conclusion is true. So if we have a true implication with a true assumption, that means that its conclusion must be true. So I have just proved for some arbitrary, that is nothing special, a number n, that it is blue. Of course, using some assumptions, these two. An arbitrary is blue. And now we may generalize. So we may say something like that. Since an arbitrary n is blue, then every n is blue. So that for each n, for each x, it doesn't matter how I call it, n or x, for each x, p of x. Is it clear? Okay. This was a correct, valid argument. And now, let's consider an invalid one. Something like that. Some number is blue. And every fragile number is blue. Then I say, what does it mean some number is blue? They exist. Could you give another example of how to prove? I'll give it now. How to disprove, how to refute. And arguments of this form will be very common in our presentation. We will see them really soon. Okay. Some number is blue. There exists a number which is blue. Every fragile number is blue. May one validly conclude from these two that some number is fragile? Is it the case that in every possible world, always, when some number is blue, whatever it could mean, and every fragile number, written here, every fragile number is blue, does it mean that some number is fragile? Now, let's formalize our assumption. By the way, b of x, as it was previously, means that x is blue. Our first assumption is what? Some number is blue. What does it mean? There is a number which is blue. And our second assumption, it hasn't changed. Every fragile number is blue. And now we want to conclude from these two that some number is fragile. What does it mean? There exists x, so that f of x. By the way, is it possible to prove it? Is it always the case that when our assumptions are true, then the conclusion is true as well? Can you imagine a world, a state of affairs, when our both assumptions are true, but the conclusion is false? What does it mean that the conclusion is false? There is no fragile numbers. Every number is not fragile. So let's construct the following state of affairs or model in formal mathematics, but we don't want to pay too much attention to these formalities. We are reasoning formally. Assume that no number is fragile. No number is fragile, and say 8 is blue. In general, it's possible. It's possible to define fragile and blue, fragility and blueness, this way that 8 is blue and no number is fragile. Then we have that is there a number which is blue? It's 8. It is the case that every fragile number is blue. Why not? Do you remember our bald king of France from the previous lecture? Every man, if he is the present king of France, is bald. Here we have exactly that. Every number, if it is fragile, is blue. But no number is fragile. So this one is false. From falsity, it follows everything. So our implication is true for whatever x. So both assumptions are true. But what about our conclusion? Is it true or false? In the world when no number is fragile? False. So we have constructed a situation when both assumptions are true, but the conclusion is false. So it is not the case that whenever both the assumptions are true, the conclusion is true as well. It's not the case. It's possible that our assumptions are true, but the conclusion is false. Is it clear? So we have proved that this one is not valid or is invalid. It's invalid, not valid. Is it clear? Now, I think that's enough for logic. And we can do some mathematics, a little bit. Of course, using our logical methods and logical formalism, quantifiers or so. So enough for logic. Let's do some mathematics. In a programmer's style, by the way, do you know what a string or list is? In many popular programming languages, you have structures such that A, B, C. What is it? It's a finite sequence of some symbols. You can also express it or denote it the following way, or maybe this one or something like that. But in general, I will omit any quotation marks. So this is a string. What is a string? Informally speaking, a string is a finite. What do you mean intuitively? What does it mean finite? Ended, of course. In 1 or 2 or 3 or 5 or 11 or 100 steps. So it has some natural numbered length. So what is a string? Informally, so another definition in quotation marks, it is not that rigorous as it would be in general in mathematics. So a string over the alphabet A is what? Is a finite sequence of symbols from A. Can you give me an example of a string over natural numbers? What is an alphabet? It's not necessary that our alphabet is, say, English or Latin or whatever alphabet of natural language. Natural numbers might be taken as alphabet. Why not? So please, give me a string over natural numbers. Something is a string over the set of natural numbers. By the way, are you familiar with this symbol? Oh. All natural numbers, 0, 1, 2, 3. Do you know this collection? Okay. So please, give me a string over the set or alphabet of natural numbers. A finite sequence of natural numbers. 3, 2. 3 is the first symbol, 2 is the last one. Why not? Of course, it's a valid example. By the way, let's use the following notation. Big S of A would be the set. Do you know what a set is? At least intuitively, some collection. So it is the set of all strings over A. So we see that it's a string from our S of A. By the way, are you familiar with such a symbol? X belongs to A. Please raise your hands who is familiar. And what about you, gentlemen? Are you familiar with such a symbol? X belongs to A. Is part, maybe, is an element, a member of some collection, belongs to a set, belongs to the set A. Is it familiar? I'm not asking for the definition, but just for some basic intuitive understanding. For example, do you agree, say, with the following? 17 belongs to the set of natural numbers. It is another way to say that 17 is a natural number. Is -3 a natural number? It is not a natural. Okay, so I may say that this sequence is a string over the set of all natural numbers, is a finite sequence of naturals. By the way, is it intuitively clear what the length of a string means? Length. How long is it? So, what is the length of this string? 2. But can you give me a string with the length 3? 1, 2, 3. That's it. But what is the length of this string? 2, 2, 4. 3 as well. So, of course, we may have repetitions of symbols in a string. But can you give me an example of a string of length 1? And what if it is not 1 but 42? That's another string of length 1. But is it possible to construct a string of length 0? It depends, of course. It depends on your definitions and so on. But in general, in programming practice, empty strings are first-class citizens. They are widely used and accepted. So we may consider an empty string. Now, by the way, the alphabet here is natural. And over any alphabet, we have such an empty string. So the empty string. So that's nice, but what if you had no strings defined in your favorite programming language? How is it possible to construct or define them from scratch? How is it possible to explain to a computer what a string is? Computer is quite dumb. It doesn't grasp what, say, length or finite or sequence. What do these words mean? Doesn't know it. It's just a computer. Can't think. But he may do something according to an algorithm. Is this idea clear? So, our approach to redefine strings in a computer-friendly manner is to provide some generating rules. Some rules which describe how to produce all possible strings. There will be two such rules. Okay, let's redefine. Strings in computer friendly way. There will be two rules. Our empty brackets denote a string. So this is a string over whatever alphabet. This is a string. It is the first rule. And the second one will be the following. If, excuse me, in mathematics we have plenty of implications. Mathematics is all about implications, about conditional statements. So if you have any hope to grasp mathematics, you must understand implications. When they true, that if the assumption is false, the implication is true. If the conclusion is true, the implication is true, and these cases are the only ones when the implication is true. So, if S is a string over A, and X is a symbol from our alphabet, if, then this thing, X, column S, is a string over A. What is column? Nothing. What is this one? Nothing, some symbol. So these are just rules, some pieces in our game. Do you know the game of chess, say? What is, say, bishop? Or, let it be, king. What is the king in the game of chess? What is his kingdom, say? It's quite pointless to ask such questions. The king is the piece that has so and so behavior according to the rules. But whether this king is a man or a piece of, I don't know, wood or metal, it doesn't matter. It is totally defined by the rules. And this idea is the essence of so-called axiomatic method in mathematics. When you do not define what some object is, you say that everything that behaves this way deserves the name of, say, natural number. And here, we likewise stipulate some rules for generating strings. And these symbols are just such pieces. Oh, okay. Now, I can state the following, a statement. 1 2 and our brackets. This is a string. By the way, we have no parentheses, no round brackets here. This is a string. Is a string over the alphabet of naturals. Why is it so? Let's prove it. Now we shall have so-called construction of this object. This is a string. By the way, we shall write belongs to S of n. For not to repeat this long phrase, is a string over n. Is it clear? We like brevity in mathematics and want to shorten our phrases. This is a string over n. Why? According to which rule? This is by our rule 1. What can you say about 2? Is 2 a natural number? So, 2 is a natural number, and this part is a string over naturals. So you may construct such a thing. Take 2, put our columns there, and then put a string. So this is another string. Why? According to which rule? According to the second rule. Is it clear? But here I have a string. 1 is a natural number. And I can construct the following thing, which would be another string by the same rule too. Is the principle clear? So I may construct every string in a sequence of steps. And this is easily programmable. You can code this definition in many languages, especially of functional kind, like Haskell or something like that. So, but now let's create more convenient notation. We will use this symbol x1, x2, comma, and so on, xn. We will use this symbol for the following string: x1, column, x2, column, x3, column, and so on, xn, column, brackets. Is it clear? For example, this can be shortened to just 1. So, this one is the empty string, of course. Of course. Just look at this one. Here we have some base, and then we construct a string in a sequence of steps. How? We just add a new symbol to it. In programming practice, these two things are known as data type constructors. These two things just construct a string in a sequence of the applications. Is it clear? By the way, we have some other rule, which is not that clear, but it is necessary. Nothing else is a string. So everything which is called string may be constructed this way. Of course, it is not that clear, but it is necessary. Our treatment is still informal, so it's okay to have such a not very clear rule. Every string is constructed via rules 1 and 2. In order to prove something about strings, I need some axioms. You know, the computer is dumb. He knows nothing. He can't think. But he can mechanically apply various rules. Let's give some rules which may help our computer to prove something about strings. Axiom 1. X1. Axiom 1 is as follows. For every x, for every s is a symbol, x is a string, it is not the case that our empty string equals any string constructed using a column. So our constructors are distinct. We axiomatically stipulate that this is not empty. Don't know what empty is. Just stipulate it. This thing is some other from this one. And another axiom is as follows. For each x, for each y, for each s, for each t, what does it mean that x column s equals y column t? When is it possible? T is, of course, it's string, as well as s, and these are symbols. But it doesn't matter. But it's not enough. When these two are equal, what do you think? Use your intuition. When two strings are equal. So in general, this is the first symbol of our string, widely known as the head of the string. And this is known as the tail of the string. So it's known as the head, and this is known as the tail. Okay, when two strings are equal, their heads are equal. It is necessary, but is it sufficient? Is it enough? What's needed also? Why? No. Two strings are equal whenever their heads are equal and their tails are equal as well. If and only if. Is it clear? And now, using these two axioms, I may prove formally, very formally, a very simple theorem. A statement, or I don't know, a lemma. Have we discussed what lemma means? I remember we have. Lemma is a little theorem. Theorem is a statement you want to prove. Okay. A lemma. This string 1, 2 is not equal. It is not the case that this string is equal to this one. Some students ask me for new examples of proofs. Now we have a chance to construct such an example. How is it possible to prove that these two are not equal? By the way, what is the most natural way to prove that something does not hold? That is, something is false. How is it possible to prove that something is false? Assume that it is true and it infer a contradiction. That is a statement which is knowingly false. What is the basis for such an argument? We know that false may follow only from false. If falsity follows, why should their tail be equal? Because they might not be empty. Why they must be equal? That's an axiom. But anyway, let's consider two strings. 1, 3, empty string, and 1, 3, empty string. Why do they equal each other? Because their first symbols, heads, are the same, and their tails are the same. Why their tails are the same? Because the heads of their tails are the same, and so on. So in general, you may not you may not distract these tails, go deeper into them. So you say that it's enough for the strings to be equal, that these are equal and their tails are equal. May these tails be equal, be empty? Of course, why not? Why not? Both, yeah, may be empty. Of course. So I haven't understood your question, by the way. So please rephrase it. What's the problem with this definition? I can't see. So we want to prove that some statement is false. In order to do that, it's enough to assume that it is true and get a contradiction, a falsity. Okay, we want this equality to be false. Do you agree? What does it mean that negation is true? Negation is true is if and only if the statement itself is false. We want it to be false. In order to prove something false, it's enough to infer a knowingly false statement. From it. So we have to infer some falsity from this equation. Assume it. Assume that indeed 1, 2 equals 1, 2, 3. Now let's recall our notation. What does it mean? So, concerning your question, Masood, the reason that the tails should be equal if they might not be empty. First of all, they may be empty. If you have any doubts, try to construct an example when our axiom fails. So, assume that these two are equal, but this one equals what? 1, column, 2, column, empty string. This equals 1, column 2, column 3, column, empty string. I see here that these two strings are equal. We shall finish in a minute. But here we may take this one as S and this one as T. We have two strings which are equal. But if these two strings are equal, that means by axiom 2, that means that their tails have to be equal. So then their tails have to be equal. Okay. But the tails are of the same form, X column S and Y column T. By the same axiom 2, that means that the tails of these two strings must be equal. So the empty string must equal this one. But this string is not empty, that is, it has column. But we have axiom 1. Axiom 1 says what? It is not the case that this string equals this one. So I have a conjunction of a statement and its negation. What can you say about such a statement? A and not A. Could it be true? A and not A. If A is true, then it is false, because not A is false. If A is false, then it is still false. Is it clear? So this one is false. This one is always false. So here we have two statements, that is their conjunction. Which conjunction is false? I have got a knowingly false statement from our equation. That means that our equation must be false itself. It is false, its negation is true. When you obtain some known falsity, you may say that you have got a contradiction. I shall use such a sign for contradiction. That means that we have got a contradiction. Contradiction is a knowingly false statement. We have got a contradiction. From assuming this equation, we have got a contradiction. Hence, the equation was false and its negation was true. Is it clear? In fact, these two axioms are very, very weak. Very weak. They don't allow us to prove anything interesting. In order to prove any interesting thing, we need another powerful axiom, which is the induction principle. For strings, not for natural numbers, but for strings. It's similar to that for natural numbers, by the way. We shall see that principle next time. And now, please tell me, who is familiar to the induction principle, principle of mathematical induction for natural numbers? So please raise your hands. You are, you, and what about you, gentlemen? Are you familiar with the induction principle? Why don't you raise your hand? And what about you? Have you heard about the induction principle? Okay, then anyway, we are going to discuss induction in every detail and solve a lot of problems about induction. Why? Because in general, induction is one of the most important proof methods, one of the most important ideas of all mathematics. Induction is of utmost importance. So thank you. If you have any questions, please feel free to ask them. Oh, dear students, if you still have any questions, you may either ask them now or use our Telegram group. So, bye-bye.